Hi there folks, hope you're all well and coping. Hopefully it'll not last too long. And but anyway, right, I was obviously the last couple of videos I was kind of going off on a kind of a maths odyssey and I realise now that we're kind of running out of time. Time is getting short. It's been harder to try and keep up and get things up than I thought it was going to be. But what I'm going to do, there's 3 outcomes for this. So I'm going to concentrate on each outcome. The first one being vectors. And this lecture should cover everything you need to know to pass the assessment. And vectors, we've done a lot of vectors before actually. In AC, the polar coordinate, changing it to rectangular, and but what I'll do is I'll just generally go over vectors, how to multiply them, a thing called the dot product, the cross product, and a couple other wee things, and drawing them out and that. Well, so I'll get to that one out. Right, this is a vector here. Say for instance a couple of forces, and the thing about a vector, it has a magnitude and it has a direction, and that is a difference, a distinction between like what they call a scalar value, which would be speed. A scalar would be like going at 50 kilometers per hour, but your velocity, which is a vector, is you're going at 50 kilometers per hour due northwest or south. There is a direction associated with it. And how do we sort of quantify what we're doing then with vectors? How do we find the direction? What we tend to do is have a reference point for the vector, and say this was, say we were looking down, and say this was your horizontal, and this force is acting up, say, into the air, and this is ground level. We would say that this is a reference point for this vector. And when we do it graphically, or what we tend to kind of stick to is saying that this is the x plane, and going up here is the y plane, just like you use in graphs and that type of thing. It's exactly the same. Now, so what that allows us to do then, we can say, well, this force has a size or a magnitude and it is going in this direction, but that direction is at an angle of theta to the x-axis here. So we've come across this many times in AC circuits, where you have a voltage, and that would maybe equal 100 volts at an angle of 30 degrees, say. And we learned how to manipulate these vectors, like if you had V1 and V2, see that was 50 volts at say 20 degrees, and we learned how to multiply these and also how to divide, and there were certain steps that we needed to do that. That's a multiplication, yeah, and also adding or subtracting, and there's a technique to both of these. Now I'm quickly going to say here is, when we look at this is what they call, this vector is in what they call polar form, where it shows you the direction it's going, sorry, It indicates the value or the size of it, or the magnitude of it, and it tells you what direction it's going. Now, say for instance this was this force here, say, I could actually just change it to voltage. I was actually going to illustrate something with the forces, but I'll do that in a wee second. So, say that was your voltage. And what you denote that, see the size of this, or the magnitude of the length, or how big it is, you denote that with these two lines either side of it. And what that means is that's the absolute value of it. No matter what direction it's going in, it's this size. And it is at this angle here. So we would write that as V1 equals the magnitude of V1 at the angle here. And that's to indicate, that's a polar form, and that indicates it's this size and it's at this angle. Good stuff. Now, what we have to think about is sometimes it's quite difficult to manipulate polar coordinates, or to use them to figure out what we want to find out. For instance, if you want to add two vectors together, you have to change this to another form. We have done this, as I say, many times in AC, and I hope you remember that we can split this vector here, this voltage here, into two separate components. So it kind of looked like that, where if this was the y direction on the graph that you're looking at this for, that means that, for instance, this component of the vector, or see the vector is composed of two different components, in this case anyway. We have and we have to remember this vector is only in this plane just now. It doesn't have any, it only has like your x and your y component, like a kind of length and a height. It doesn't have any depth at this point. So in other words, it's not a 3D vector. So it only has two components. It has a component in this dimension and a component in this dimension. And we're going to call that the x dimension and the y dimension, or the x coordinate and the y coordinate kind of thing. So what we say then is, we say, well, this value along here and this value of component along here can combine to give us this and that. Now this is an old thing that some Greek philosopher came up with years ago, a guy called Pythagoras. We went over this again. I hope I'm not repeating myself too much. Where this part and this part can be added to this part, and what happens is we get like a right angle triangle here, and that makes it much easier for us to handle being engineers. And one thing, being an engineer, see, triangles and circles, they are engineers' best friends. They're so useful in all applications. This rectangular thing, what do they call these? They call these the rectangular components of this vector. And so this x component and the y component will combine to give us this. Now I hope I'm not being too long-winded with this, but essentially this is a Pythagoras triangle. You have a length here and a length here, and this is like your x component of it, and this is your y component of it. You would say that there should be 30 of the x part, or 30 going along this direction, and it would be 40 going up in this direction. So in other words, that would be 30 along the horizontal plane and 40 in the vertical plane. And the resultant of that look like that, just like what we've been doing. So what I'm trying to say here is the vector, this is like plotting coordinates on any sort of kind of graph. So for instance, right, say we had x and y, 2, 3, 4, 5, 6, 7, like that, right? And -1, -2, -3, -4. Now, say you had a vector, say A, and its coordinates were 3, 5, say. That means you go along the x, this is the x component, that's the y component. You go along 1, 2, 3, and then you got 5. 1, 2, 3, 4, 5. So the x part would be there, the y part would be there. The resultant vector would look like that. And this angle here, you'd work out by using this tan to -1 of the opposite of 5 over 3. You get a thing called an Argand diagram. It's very similar to this. In fact, it's exactly the same basically. If you're asked to, say you're given a vector 3, 4 again, go along 3, up 4, or if it was -2, -5, that would be -2, -5, it kind of look like that. You'll get asked to draw a few of these out. Very simple, really. Now, what I was going to say is, well, we've got this kind of convention with vectors, where you call this part the I part and that part the j part, and that is like the x and the y part. Right. Now, I'm going to quickly just add something to this here. Now, say we've got a diagram like that. You're going to have your x component, like your length. This is like your height. Now, in the real world, you're going to get a depth. Kind of goes along like that. And that's what they call the z plane, the z axis. You can imagine like if this is like a kind of 3D box like that. That would be your x component, that's your y, and this bit down here is your z. And that gives you your 3D, that uses all the dimensions. So for instance, you might have a vector that goes along here, say it goes along 3, it goes up here, say 5 again, but then it will go along this direction. So you'll have an x component, a y component, and actually call this a, x component and a z component. So if you wanted to, so if you had a 3D vector, you simply just add this z component to your coordinate system here. So say, let's see, we had a force, say, and this force was, it went along here, up that way, and it's moving back, just kind of like this here. You would say, it went 3 along the x axis, and it went 5 up the j or the y axis, then it went, say, back 7, and we call this k, I, j, k, or this is like the x, y and the z part. They just use different kind of what do you call it, nomenclature, different ways of identifying these. Like engineers tend to use, mathematicians will use I, j, k. But anyway, right, so there's certain things about that are very similar to this, but just slightly different. I hope I'm not being too long-winded there. I know you know what vectors are, and what I'm going to do here is I'm just going to start doing a couple of wee examples using the vectors, and then we'll just kind of go from there. Hopefully it'll make sense. Right, we've got two wee vectors here, 3, 6, 5 and 8. That's your I, your j, your I and your j. And this would, let's say 3 up 6. And this one's 5 up 8. Something like that. Right. Now you can say you said to yourself, what would be the addition if you wanted to add these two forces together? What would be the total force there? And remember, these parts here, that's like your rectangular parts. Remember, this is like your x and your y, or your I and your j. So if you want to add these, you can simply add the components here. So if he says F, the total force of F1 plus F2, that would be 3 plus 5 and 6 plus 8 would equal 8 over 14. So if you were to add them together, tip to tail, remember if you have a vector like that, and you have, say, another vector like this, and another vector, say, like that, if you were to add them together, you add them sort of tip to tail. So you go from the starting point to the tip, and then you would add, if you were to add this one to it, you would add it from that tip to its tail. And again, if you were to add this part to it, and what you've ended up with is this, what they call the resultant, and that is the combination of these three vectors, say for instance. And what you find is if you add the x components and the y components together, the resultant vector you get is the resultant vector. Whereas the polar coordinates, you cannot just add polar coordinates. Right, so what we're saying here is you can just add your vectors as long as you just add the individual components to each other. But also, say you wanted to say, right, I want to increase F1 by, say, 3 and F2, we could times that by, say, 2, say. So 3 F1 would equal 3 times 3I over 6j, which would equal 3 times 3 is 9I over 18j. And 2 times F2, I wonder if you can you see that? 2 times F2 would equal 2. What's F2? 5I plus 8j. That equals 10I over 16j. So if you multiply the magnitude, or this vector here, it's gonna, you just simply multiply each component by however much you're multiplying it by. And if you want to add these again, say you want to add, well, what would 3f, can you see that? 3f1 plus 2f2 equal? That would be 9I over 18j plus 10I over 16j. 10j 16, right. And again, simply add them, so it would be 19I over, what's that, 34 j. I hope you can see that. Now if we have a 3D coordinate system, so you had another, again, force 1, and this was 3D, so say it was 5i, I'll do it like this, 5i and say 4j and 3k, and f2 was equal to say 3i, 2j and 2k. You do the exact same thing if you wanted to say I wanted you to find f total would be, you just add these, so that would be 8i, 6j, 5k, and again say 3f1 is going to equal 3 times 5 15, 3 times 4 is 12j, 3 times 3 is 9k, and 2f2 would be 6, can you see that? 6i, 4j and 4k. Right, well that makes sense. I'm going to show you a thing here, it's called collinearity about vectors. So we'll just get into that. So you've got 3 vectors here, and I'm just doing this in a 2D plane, not the 3D one, just to make it a bit more clearer what's going on. So say you've got this one, vector A goes along 2 and up 1, it's sitting there somewhere, vector B goes along 4 and up 2, and then vector C here goes along 6 and up 3. Right, so we've got points, that vector goes like that. Can you notice something about these vectors? They all go through each other. That means what they call is they're collinear, and if you notice these, they obviously go up at the same rate or the same ratio. So in other words, that's like 2 times that, and that's like 3, so that's like 2 times b, and that's like 3 times b, this one. And you could say well, if that was this is actually a point that lies on this whole vector b, this part here. Now there's a way we can kind of check this, right? We can say vector a b, what we do, equals vector b minus a, right? And what we're doing is we're saying that'd be 4 minus 2, makes the 4 component out here, or the I part out here, minus the I part there, and that's going to equal 2, and this bottom part, 2, the same again, the b minus a, 2 minus 1, that equals 2, 1, which is the same as that. So basically it's just a kind of multiple of it. And again, if we look at the difference between these two, we'll say, can you see that there? We'll say this vector b, bc would equal vector c minus vector b. And let's see, what would that be then? That's going to be 6 minus 4, 3 minus 2, which again, 2, 1. So you can see the connection there. They have the same, it's like they've got the same gradient, the same rate of change. And so what you'll find is if you, any point along this line, say for instance you picked 4.5, that would follow the same kind of ratio. So what is that then? So what would 4.5 be then? So if we're going up at 1 and that's 2, if that was 4.5, that's going to be half of that. So if that was 4.5, or say for instance, right, if you went along there 9, the I part is 9, so that's 2, so the j part is going to be half of that, so that'll be 4.5. So if you went along to 9 there and you went up the way, that'd be 4.5. Just the same as this is 4 and that's 2, or this is 2, that's 1, that's 4, that's 2, that's 5, that'll be 2.5. 6 is 3, 9 is 4.5. Just like this is twice. So what it's saying there is the x component is always 2 times bigger than the y component. And that's just for this individual case here, obviously. So let's have a look then. Say we do another quick one. Say again, it was in fact I'm just gonna do an example with a 3D vector, right? So say we've got v1 and that's equal to 4i 5j 6k, see, right? And we've got another vector v2 is going to equal, let's see now, right, we have 3 vectors, v1 4i 5j 6k, 8i 10j 12k, 32i 40j and 48k. Now we want to find, firstly we want to find if these do lie in a straight line. In other words, are they part of the same vector? Right, so let's have a look, see. So say we say, well, v1 v2 is going to equal v, say, we'll say v2 that's v1 as such. So we're going to say that's 8i, because that's v2, 8i minus 4i, and 10j minus 5j, and we've got 12k minus 6k. And what does that equal? That's going to be 4i, oops, 5j, full enough, and 6k. Well, that tells us that these are definitely lying on the same plane. Let's have a look at this pair here. So v3 minus, well, v2 v3 equal v3. Wait a second, Alan. In fact, I'm just gonna do an example with a 3D vector, right? So say we've got v1 and that's equal to 4i 5j 6k, see, right? And we've got another vector v2 is going to equal, let's see now, right, that's going to be, it'll be 32 minus 8i, 40 minus 10j, 48 minus 12k, which is going to equal 32 minus 8 is, what's that, 26, is it? 24, 30j, and it's going to be 36, is it? Yep, 36k. Right, I don't know if you can actually see that there. So what we've got here, see, finding the difference between
v2 and v3. That gives us 24, 30 and 36. Now this one here, the difference between v1 and v2 gives us 4, 5 and 6. You might say, well, I don't know, like, I don't know if they're on the same line. Well, they are actually, because see, if you can take what they call a common factor out here. See, there's 4 there and 24. How many 4s go into 24? That's 6. Right, how many 5s go into 30? That's 6. How many 6s go into 36? That's 6. So you could say then that this v1, v2, which equals 4, 5 and 6, I, j, k, is the difference here then is that is like 6 times v1, v2, because if that was the case, it would be 6 times 4 times 5 times 6k. That's all that really is there. That, what they're saying is that's a vector that goes along 5. Can you see this? Goes along 5. Sorry, it goes along 4, up 5, and down this way 6. So you're left with a vector that kind of looks like that. This one here, this vector here, the one that comes out of that, all that is it's as if you've multiplied this by 6, or made it 6 times bigger, so it's going along 24, up 30, and along 36. So it's basically this same vector, it's just extended much further out. So that means it's got the same kind of gradient, it's going in the same direction. So these, your x, j and your k components all change at the same sort of rate. So it is basically that kind of like is that vector, it's just 6 times bigger, or it's much further out on that line that vector makes. All that's making sense. So that's what they call collinear, and you'll find that any point along this line, like that would be that could be like 8, 10, 12, or 40, 50, 60, 120, no, see 80, 100, 120, that kind of thing. I really hope that's making sense. I hope that's making sense. See, a lot of stuff we're going to do, you've done before actually. The questions and assessments are very closely related to some of the stuff we've done before. There's a couple of new things we need to look at. A thing called the cross product and the dot product. And so say it's very closely related to the stuff we've done in AC. But I hope that you understood that collinear thing. And I'll do another little example of that before the end of this video. Okay. First thing we're going to look at here is a dot product. This is kind of like multiplying these in a way. And what we do here, I'll just go through the procedure with you. If this is force 1 and this is force 2, wait a sec. So when you find the dot product here, you simply multiply each component to its corresponding component. Wait a second. Sorry. Where are we? So this I, j, k, I, j, k. When you do the dot product, you multiply the corresponding components and you simply add them. So this f1 dot f2 would be equal to 3 times 6, and that's the I component, plus minus 2 times 3, which is a j component, plus, right, and this last bit would be 8 times minus 2, so that's 18i, and minus 2 times 3 is minus 6j, this is a k bit, minus 16k. Sorry. All that commotion. Sorry. Well, it is that actually. You could just say it was that. This is like just saying it's the components of it. But you just simply add them, so it'd be 18 minus 6 minus 16, which equals, what's that, minus 4. And this is a scalar value. In other words, it's just a number. It's a kind of phenomenon that happens when you get the dot product of any vectors. You'll get a scalar value out of it, i.e. just like a magnitude. Okay. Now I'm going to look at the magnitude here and show how it's a similar thing you do to get the magnitude of a 3D vector. Okay. Again, our old friend Pythagoras. That's your adjacent, your opposite, the hypotenuse. If you want to find the magnitude of this, you square that and square that, add them, and get the square root. For instance, if that was 3, that was 4, you would say what's h? H would equal, can you see that? The square root of 3 squared plus 4 squared, which equals the square root of 25, which equals 5. So 3, 4, 5. Now, so if we, this is kind of saying you've got that there would be a vector like that, 3i, 4j. Now, if you have a vector 3, 4, and say 8, I, j, k, to find the magnitude, say this was z, say, for I'm just saying, so say it was an impedance, and the magnitude would equal the square root of 3 squared, this first part, plus 4 squared, the j part, plus 8 squared, the k part, I, j, k. Can you see that? Right, there you go. So it's exactly the same as that, except you're just adding this extra component here. So if you want to find the magnitude, let's do one. Say you want to find the magnitude of, say you had, what was that, z1, and that was equal to 369, say, I, j, k. Now we want to find the magnitude of that. Would equal the square root of 3 squared plus 6 squared plus 9 squared. So that's going to equal 9, 36, 81, and it's 126. Square root of that, sorry. Which would be, I know 1, 4, 4 is 12, so let's see. So that's 11.225. Whether it's meters, centimeters, whatever. So you can see it's very similar to looking at a 2D or an I and a j vector to find the magnitude. It just so happens to have another component in another dimension. So you just have to include that there. So I'm just going to quickly here look at this other one. Right, so we've got this first impedance here, and we've got an impedance 2 here. So in other words, you've got two vectors here. This one here, 369, we've worked out, we'll call this, well, if it's an impedance, it'll be ohms. And then this one here, let's do the same. Let's find out what Z2 is. And that's going to be square root of 2 squared plus minus 4 squared plus 6 squared. I'll work that out. So that works out the square root of 56, which equals 7.5. We'll just round this one up to 3 actually, 11.3 ohms and 7.5 ohms. Okay, hope you can see that. Just getting the magnitudes of these, right? Now, what do we always have in AC? We always have an angle lurking about there somewhere. So we're going to figure out how we're going to find out between these two vectors what the angle is going to be between them. Okay, right. Oops. Right. We need to work out another thing as well for these two vectors here. We want to work out the dot product. I'll do it here actually, we've got enough room here. So the dot product Z1, Z2 dot. And that is going to equal 3 times 2 plus minus 4 times 6. Hope you can see that. Minus 4 times 6 plus 6, which is 54. So that's going to equal 6. 24, that's minus 24 plus 54, which equals 36. Remember, that is just a number, the scalar. Right, we can actually use this information to find out the angle between these two vectors. So I'll try and kind of roughly sketch these out. X, Y, Z. So this one was going along 3, went up 6, went back 9. So it's like, that's kind of like going like that. But we can kind of imagine that. And then this next one is going along 2, up 4, and along 6. So it's kind of going out like that. Now, what we are wanting to do is find out this angle between the two vectors here. Right. Now, I'm not sure what that angle is, but we'll see what this works out at. I've just randomly picked these numbers, by the way. So I've not looked, I've not pre-checked them or anything. I've just, so it'll be quite interesting to see what that angle really is actually. So there's a formula that you can use for this. Now, this is angle theta, mind. So cos of theta is equal to the dot product of 1 and 2 divided by the magnitude of 1 times the magnitude of 2. So what was that then? There we go, that was 36 was the dot product, and the magnitude of that was 11.2, well, no, it was 11.3 I just said, times 7.5. What does that equal? So that equals 0.425. And so, like when you find the angle when you're looking at the opposite and the adjacent, you find the inverse tan. What we're finding here then is the inverse cos. So it's cos to the minus 1 of 0.425, and that comes out at 65 degrees. So I've drawn it not that great there, but this angle here, it's probably more, I don't know, that should be 65 degrees. Now I hope that makes sense. And if you look at this bit here, what is the cos again? That's adjacent over the hypotenuse. So this here is kind of equivalent of the adjacent, and this is equivalent of the hypotenuse. But that's another story, and we don't need to get into that just now. We just need to know how to work this out. So what we're doing here is we get the magnitude of each vector, we get the dot product, we divide the dot product by the sum, the multiplication of the magnitudes here, and what that does is it gives us the cos of this theta, which was 0.45, and then we found the inverse cos, and that gives us our 65 degrees. Hope that's making sense. I'm gonna go over another few things. I know it's dragging on a little bit, and you know what, I think we've kind of covered most things. What I'm going to do is go through a few examples here, so bear with me. And there is one thing we need to check out though, I forgot about that. Right, 2 seconds. Right, see, we've got a polar value and a rectangular value. So let's have a look. See, we've got 3 plus, I don't know, 4j again, right? 3i plus 4j. And we want to divide that by, say, 2 minus j. So 2 minus 1j. Right? Now, I'm just going to quickly run over the rules again. So if you have a voltage with a magnitude and an angle theta, and you have another voltage 2 at an angle theta 2, theta 1. So see, if you want to multiply them, so if you want to multiply, you say V1 times V2 is going to equal V1 times V2 at an angle of Q1, theta 1 plus theta 2. So when you multiply them, you add the angles. And if you divide V1 over V2, you divide the magnitudes and you subtract the angles. Theta 1 minus theta 2 gives you the angle. The thing is, you can't add polar coordinates, and you can't subtract them either. So if you want to do that, you need to change them. You need to change from polar to rectangular. Because what you need to do is you have to add the components of them. You have to add the I bits or the X bits. You have to add the J bits or the Y bits or the Z bits and the K bits. Right. So then we're thinking about a situation here where you have the rectangular components of it, but you still have to divide it. So imagine you can't turn this into polar, just for whatever reason. Maybe the computational side of maybe a system that needs to have your J and your I inputs, I don't know, something like that, but you need to divide these, but not by not putting it into polar, right? And also you'll get a situation where we're going to have is 3i plus 4j times 2i minus j. The first one I want to quickly look at is this one, right? Well, in fact, you know what? I'll quickly look at this. Remember when in one of my last videos we were looking at brackets, and if you're multiplying brackets out, you would say this one times that one, this one times that one, this one times that one, this one times that one. Do you remember that? So, and in fact this is closely related to this actually. So if you did multiply that out, that would be 3i times 2i, so that would be 6i squared minus 3ij plus 6ij minus 4j squared. Now this has made me think about something that we've not even looked at in this, but one of the things that underpins all this, what they call the J notation or complex numbers, is the fact that, and what is it, sorry, mathematicians call them imaginary numbers. And the reason they call it an imaginary number is J is equal to the square root of minus 1. And therefore the square root of minus 1 doesn't actually exist. I know that might be a little bit hard to comprehend and get your head round. So, because if you ever get minus 1 times minus 1 equals plus 1, or minus 1 times plus 1 equals, oops, that is minus 1, plus 1 times plus 1 equals 1. Now, you don't have to get too deep into this, but when you multiply these I and j brackets out, and you'll find you'll get a bit here that will say j squared. Because j is the square root of minus 1, whenever you get a j squared, the j squared equals minus 1. So, looking at this then, and not to complicate anything too much more, but an I is equal to 1, or the square root of 1. Anyway, let's not get too hung up on this. So if you imagine, what we've done there is we can say that'll be this I squared, sorry, this I is a root 1. Now I squared equals 1. Sorry, it's even more simple than that. I mean, I is 1, even if it is squared, it's still 1. So, looking at this then, that's just going to have a value of 6 times 1 minus 3 times 1 times j plus 6 times 1 times j minus the square root, sorry, j squared, which is minus, so that's going to be plus 8. So what you're going to be left with, when you multiply them across, multiply that bracket by that bracket, we're going to have 6 minus 3ij plus 3ij, so that's going to be plus 3j. Now we can kind of disregard the I here really, because it's just 1, or even if it's squared it's 1, whatever happens to it, it's just always 1. So, and let's see this bit here, j squared, so that's plus minus 4 minus 1 plus 4. So you multiply these two together. Well, plus 4, you can just add that then, I suppose, obviously. That's going to be 6 plus 4. It's going to be 10 plus 3j. So what you do is you multiply this by that, and you're left with a vector. I hope you can see that. Right, now what I'm going to do, we have to consider another situation here where I'll just use the same values again. What was it? 3i plus 4j divided by 2i minus j. Right. I'm just going to cut to the chase here. You got a thing called the conjugate, right? And the conjugate is, say you've got 2i minus 1j. Right? The conjugate is 2i plus j. What that is you just change the j part. What the sign before the j part. So if that's negative there, you change it. So say we used this when we looked at power, or apparent power anyway. This equals vi conjugate. We changed the current was what, 30 amps at 30 degrees minus 30. You would change that to the conjugate would equal 30 plus 30. I'm sure you remember that. So there's another thing that goes on here, which is we multiply this, right? But the thing is, it seems really bizarre actually. But when you multiply this by 2i plus j, right? You multiply this bottom bit by the conjugate, but you can't. It's like an equation. You can't just multiply the bottom bit. You have to do the exact same thing to the top bit. So you multiply it by 2i plus j, top and bottom. And that seems really odd. That, what, like, how can you do that? Because that doesn't actually change it, and you know why? Because if you have 2i plus j over 2i plus j, that equals 1. So it doesn't actually really change that. It does change it though when we do the maths and algebra, but really all you're doing is multiplying this by 1. It's quite odd thing to think about. You could multiply this by 37a squared plus 42xy cubed divided by 32a squared plus 42xy cubed, because you can multiply this by that, because that is actually 1. If you divide that by that, that's 1. Anyway, I'm not going into that too deeply, but it's quite an odd thing. But totally intuitive once you think about it. Now there is a characteristic about this thing, multiplying a conjugate. The conjugate having your I and your j part multiplied by the I and the j part, but the j parts are the opposites of each other. And I'll show you what happens here. So let's do this bottom bit. 2i minus j times 2i plus j. What happens here is you get 2i times 2i, that's 4i squared, plus 2ij minus 2ij that's minus j squared. Right. Now what's happened there? Firstly, these are going to disappear because 2ij minus 2ij plus 2ij minus 2ij is going to equal 0. And you're going to have 4I squared minus j squared. And what's j? J squared. Remember, j was the square root of minus 1. So if you square that, you're going to get minus 1. J squared equals minus 1. And what's I squared? Remember, I was just 1 anyway. Whatever happens, I is 1. Because it's positive 1. So what you're going to have there is 4 minus 1, which equals 5. 3. So what happens is, this is a really handy thing to do, because what you're actually doing is you're not changing this equation really, but you're changing it into a different format. And what that is you take away any complex or imaginary numbers from the bottom, and you're just left with a scalar value at the bottom of this. I'll show you what I mean. Right, so I'll do an example. Well, we'll just do this example. So that was what? We said that was 3. This came out of that. So what does the top come out of? That'll be 3i plus 4j times 2i plus j. So that's going to be 6i squared, 3 times 2ii squared plus 3ij, that's 3i and that j, plus 8ij plus 4j times j, 4j squared. So looking at that, what is that going to be? That's going to be 6 basically, 6i squared, whatever, plus 11ij plus 4, because my j squared is minus 1, so it'll be minus 4 in fact, sorry. So that's going to be 2 plus 11i. Is that right? Oh, I, because I is 1 obviously, so that's going to be 2 plus 11j. Now to finish this off though, remember this bit we worked out here is these two bits being multiplied, and this bit we worked out down here, this what is it, 2 plus 11j, that is this part. Okay. So we still need to divide it, so simply what was it? It was that over that, so it's going to be 2 plus 11j divided by this, the denominator there, which is 3. So that just simply is 2 over 3 plus 11 over 3. It's going to be 3 plus 2 over 3 j. Maybe you can see that. Hope all that's making sense. I'm just going to quickly rattle through a few things here, and I'll hopefully have this wrapped up in a few minutes. We'll do a quick example here. If you had the impedance and it was in the polar form, it was 7 plus 4j, say, right, and we're going to express this in polar. So we have to find the magnitude, which is the square root of that, the square root, that squared plus that squared, the square root of the sum of them equals that. I hope you can see that. It's not very well drawn. Now that is going to equal 49 plus 16, so that's 65, square root of 65. You can see that, which is just over 8. Now the angle, what's the angle going to be? Remember, z's like that, this is kind of like that, where this part's 7, this part's 4, Pythagoras. So to find the angle there, theta, is going to be tan to the minus 1, 4 over 7, which is going to equal 29.7 degrees. So 7 plus 4j, and rectangular is the equivalent of 8 at an angle of 29.7 degrees. Now the thing is, I'm saying that's 29.7 degrees, right? You might be asked, what's that in radians? Right? Now, the quickest and easiest way to think about this is, like in single phase, and then is 2 pi radians equals 360 degrees. So if you divide the 360 by 2 pi, and this side by 2 pi, left hand right side, left hand right hand side, it gives you a radian, and that equals 57.3 degrees. So if you were to ask, say they said, and the radian you always just donate it as pi radians, right? So it's kind of like a derivative of, right, that's it. So pi radians is equal to 180. And you might have a thing that will say, you might have a polar coordinate that says 8 at an angle of pi over 3. What that is equivalent of is dividing that by, so that's kind of like 60 degrees. 8 at 60 degrees. It's kind of like that. Now in this situation here, what we've got is 29, say that's 30 degrees, so we'll just say that's 30 degrees. It's close enough. If pi radians, so you've got pi radians equals 180 degrees, and this equals 30. So what you've got there, sorry, I've got this kind of, to get that show, it'd have to kind of be like that. Wait a second. Try and make this a little bit easier. So every radian is 57.3 degrees. Okay, so let's see, what is this? This is 30. Or we'll just, so let's see, so the amount of a radian this is 30 divided by 57.3 is going to equal, that's 0.524 of a radian, right? And we know 1 radian is 57.3, so if you multiply 57.3 by 0.524, you're going to get 30 degrees. I really hope this is making sense. Now, so if you have 30 degrees and pi radians is 180 degrees, forget about that. Let's see. Well, we can just kind of use a, so say that's the same as 3 divided by 18. You've got a 6 there, so that's going to be 1 divided by 3. No, 1 divided by, sorry, I meant 1 divided by 6. So if you were to say, if you had pi radians equals 180, if you said you had pi divided by 6 radians, that's 30 degrees. I'm really hoping this isn't overcomplicating it for you. So if you go around a full circle, 2 pi radians, or 6.28 times 57.3 is going to equal 360 degrees. Actually, you know what? I'm just actually going to tell you what a radian is. Right, so see if you have a circle, and you have the radius, and you have you rotate this round this way until, see this length of this arc, see once this becomes the same length as the radius, and obviously this will be the same length, this angle here is the angle you get when this length is equal to this length. And it's quite handy, isn't it? It's 57.3 degrees. It's really handy when you're looking at rotational devices, and I mean the cosmos and the celestial systems are all kind of dictated by rotation and spheres and circles and things. So this is a very handy ratio actually we've got here. And as I say, 2 pi, because to get the circumference, this is 2 pi times the radius, 2 pi r. So if you can imagine this radius value has just actually been turned into 57.3 degrees, and you multiply that by 2 times 3.14, you're going to get 360 degrees, which is all the way around. I'm hoping that's making sense. So let's have a look at this then. So say you went round 90 degrees or something, so pi radians equals 180 degrees. See, when you write this as well, you tend to neglect to write an r in, you just write a pi in. So say that was 90 degrees, so you would say, well, 90 degrees would be pi over 2, would equal 180 over 2, which equals 90 degrees. So if you wanted to, so the angle of pi, say that was theta, pi over 2 equals 90 degrees. Or if you had pi over 6, that would equal 180 degrees over 6, which would equal 30 degrees, which we just worked out. Or you could even have pi over 10 possibly, and that would be 180 over 10, which would be 18 degrees. And the only difference when you're using this is when you use your calculator, you have to change it to radians, so it knows you're not looking at degrees, you're looking at radians. I really hope that makes sense. And actually, you know what, I think that's just about everything you need to kind of know for this. What I'm going to do, I really hope that made sense. What I'm going to do is I'll send out a tutorial with this, and if you've got any questions, get back to me as quick as you can. And I'm going to do the other one tonight, hopefully, and I'll have it sent out to you tonight, and you've actually covered lots of it already in the last couple of lectures, so it should be no problem. Thanks for listening.